Hello friends, myself Naliniganta Jana, Senior Lecturer in Physics, Bharaneshwar Mahavidyalaya, Utkal University. Our today's topic is power dissipation in forced vibration. That means, what is power dissipated during a forced vibration? Generally, what happens in case of forced vibrations? The body executing harmonic oscillation absorbs energy from the external driving force, which is dissipated in doing work against the resistive force, and hence oscillation is maintained. That means, in forced oscillation, the vibrating body absorbs energy from the external driving force and dissipates it against the resistive force to maintain undamped oscillation. Hence, the instantaneous power absorbed by the oscillator is nothing but the rate of doing work, that is, the power dissipated is P is equal to F into V, where F is equal to applied force and V is equal to velocity of the oscillator. But we know that the applied force F is equal to F0 sin Pt. Let this is equation 1 and this is equation 2. F is equal to F0 sin Pt and V is equal to dy by dt, where y is the displacement of the particle executing SHM at any instant. But already we know that this y is nothing but y is equal to F0 m divided by root over of 4 k square p square plus p square minus omega square whole square into sin Pt minus phi. So, V is equal to dy by dt, which is equal to F0 m p by root over of 4 k square p square plus p square minus omega square whole square into sin Pt minus phi. By taking the derivative of y to get V, here sin Pt, the derivative of sin Pt will be cos. This is cos Pt minus phi into P, and here we have written P. Now, putting these values, let this is as equation 3. Now, putting these values of F and V in the expression for power, we can write. Now, putting the values of F and V from equations 2 and 3 in equation 1, we get P is equal to Fv is equal to F0 sin Pt into F0 MP divided by root over of 4 k square p square plus p square minus omega square whole square into cos pt minus phi. Now, rewriting, we can get p is equal to m f0 square p divided by root over of 4 k square p square plus p square minus omega square whole square into sin pt into cos pt minus phi. Okay. Here this is cos pt minus phi can be written as cos pt into cos phi plus sin pt into sin phi. So, rewriting this here we get this can be written as cos pt into cos phi plus sin pt into sin phi. Now, multiplying this sin pt in these two terms we can write m f0 square p by root over of 4 k square p square plus p square minus omega square whole square into sin pt into cos pt into cos phi plus sin square pt into sin phi. But over a period of complete oscillation, the time average of the integration sin pt into cos pt dt is equal to 1 by 2t integration 0 to t sin 2pt dt, which is equal to, let this equation as 4 and this equation as 5. Again 1 by t integration 0 to t sin square pt dt is equal to half now taking the average power and putting the values of equations 5 and 6 in equation 4, we can write P average, because here we have taken the average, and so your P will be written as P average will equal to M f0 square P divided by root over of 4 k square p square plus p square minus omega square whole square into this will be termed as 0 plus half sin phi, and hence we can write this as P average is equal to this much into this much, and let this equation as 6. But but tan phi, as we have discussed, is equal to 2k divided by 4k square p square plus omega square minus p square whole square, which implies sin phi is equal to 2kp divided by 4k square p square plus omega square minus p square whole square. So, putting the value of sin phi from this equation 7 in equation 6, here we can write P average is equal to m f0 square p divided by root over of 4, sorry, this is p square minus omega square, here it is p square minus omega square. So, m f0 p by 4 k square p square plus p square minus omega square whole square into half into sin phi is 2kp divided by, here is the root over 2kp root over of 4 k square p square plus p square minus omega square whole square. And rewriting this, 2 get cancelled, here this is multiplied with this, the root over gets cancelled, and hence we can write this as P average is equal to m f0 square p square k divided by 4 k square p square plus p square minus omega square whole square. And this can be written as is equal to m k into f0 square p square by 4 k square p square plus p square minus omega square whole square. But from the expression for velocity, we know that this is the square of the resonant velocity. So, P average is equal to m k v0 square, where v0 is equal to f0 p by root over of 4 k square p square plus p square minus omega square whole square. So, this is the expression for the average power dissipation during forced vibration. Now, let us discuss the probable cases, special case. The power dissipated will be maximum. Power dissipated will be maximum when the denominator will be minimum, and the denominator will be minimum when this p square minus omega square becomes 0. That means power dissipated will be maximum when the denominator becomes minimum. And this is possible. This is possible. This is possible when p square minus omega square becomes 0, which implies as p is equal to omega. Thus, the maximum power dissipation occurs when p is equal to omega, that is the applied force angular frequency is equal to the angular frequency of the vibrating body. That means, in all our discussions we have seen that resonance occurs only when the frequency of the applied force coincides with the natural frequency of the vibrating body. Also, exactly in the similar way, the average power becomes maximum. That means, the power dissipation becomes maximum when p is equal to omega. Now, let us discuss quality factor of forced oscillation. Let us discuss what is quality factor of forced oscillation. The quality factor of a forced oscillation is 2 pi times the average energy stored divided by the energy dissipated per cycle. That is quality factor is equal to Q, which is equal to 2 pi times average energy stored divided by the energy dissipated per cycle. Energy dissipated per cycle. Which is also equal to 2 pi into average energy stored divided by average power dissipated. Now, to calculate quality factor, we have to calculate the average energy stored and the average power dissipated. Already we have calculated the average power dissipated. Now, by calculating the average energy stored, we can calculate the quality factor of forced vibration. Let us now calculate the average energy stored. But the total energy of a vibrating body in SHM is equal to the sum of its kinetic energy and potential energy. So, to get the average energy stored, first we have to calculate the total energy of the vibrating body in SHM. But total energy is equal to capital E, which is equal to sum of kinetic energy and potential energy. Which is equal to half mv square plus half ky square. But we know the expression for V, hence we can write here as half m into Pa cos Pt minus phi whole square plus half m omega square y square. But the average values of cos square function and sin square function over a complete cycle is half. This can be written as half m p square a square cos square pt minus phi plus half m omega square y square. But the average value of cos square pt minus phi and sin square pt minus phi over a complete cycle is half. So, this expression now becomes as half m p square a square into half, because cos square pt minus phi is half, and this becomes 1 by 4 m omega square a square, because by putting the value of y is equal to a sin omega t, that is a sin pt minus phi, and the square of y square will be a square sin square pt minus phi, but the value of sin square pt minus phi over a complete cycle is half. So, this term becomes as half m omega square into half a square, which is equal to 1 by 4 m omega square a square. So, E is equal to 1 by 4 m p square a square plus 1 by 4 m omega square a square, which is equal to 1 by 4 m p square plus omega square into a square. This is the expression for the energy stored, and PAVG already we have calculated, it is m k f0 square p square divided by 4 k square p square plus p square minus omega square. So, this reduces to m a square p square by 2t, where t is equal to relaxation time, which we will discuss later. What is relaxation time? Let us find out the quality factor, because for quality factor we have already discussed. We have to find out the average energy stored and the average power dissipated. Now, we have calculated these two. So, quality factor is equal to Q is equal to NO stored 1 by 4 m p square plus omega square into a square divided by m a square p square by 2t, which implies Q is equal to half get cancelled, square cancelled, half p square plus omega square by p square into Pt. At resonance, P is equal to omega. So, Q is equal to half 1 plus 1 into omega t, implies Q is equal to Pt is equal to omega t. This is the quality factor of forced oscillation. Here we have finished quality factor of a forced oscillation and the power dissipation. And in deriving the expression for the quality factor, we have introduced the term T, where T is nothing but the relaxation time. Let us discuss now what is relaxation time. Okay. Let us discuss some important terms connected to damped oscillation, and these terms are relaxation time, modulation or decay constant, and quality factor, as we have already considered. These are the terms connected to damped oscillations. As quality factor is discussed, let us discuss relaxation time and damping constant. Then what is relaxation time? Relaxation time is the time interval during which the velocity reduces to 1 by e times, that means 0.368 times its initial value. Once again I am repeating, in case of damped vibration, the amplitude gradually decreases, the energy gradually decreases with time, and also the velocity of oscillation gradually decreases with increase in time. As time increases, the velocity of the vibrating body decreases in damped harmonic oscillation. So, the time interval in which the velocity of the vibrating body reduces by 1 by e times the initial value of the velocity is known as relaxation time. That means at t is equal to Tr, where Tr stands for relaxation time, V becomes V0 by E, where V0 represents the initial velocity. Initially, the velocity is maximum in damped harmonic oscillation, and with the passage of time, the velocity gradually decreases, and that time will be considered to be relaxation time when the velocity becomes 1 by e times V0, the initial velocity, that is 0.368 V0. Okay? But from the discussion of damped vibration, we know that the force acting on the body is opposed by the resistive velocity, resistive force which depends on the velocity. That is, for damped vibration, m dv by dt is equal to minus rv. Previously, we have discussed this dv by dt, which is nothing but your acceleration, but we have discussed this term as d square y by dt square, and also this v is nothing but dy by dt, and previously we have discussed during our damped vibration discussion that this term is dy by dt. Now, rewriting this, we get dv by dt is equal to minus r by m into v, and implies dv by v is equal to minus r by m into dt. And when t is nothing but your relaxation time, then this velocity becomes v0 by e. Here, if we write t as Tr, which is nothing but the relaxation time, which is equal to m by r. So, here r by m can be written as 1 by Tr, but Tr is equal to m by r is equal to relaxation time. So, this becomes as dv by v is equal to minus 1 by Tr into dt. R is the subscript and Tr is the time of relaxation. Now, integrating this equation, we get integration dv by v is equal to minus integration 1 by Tr, r for relaxation, into dt. Implies the integration of dv by v is log v, which is equal to minus 1 by Tr dt will be expressed as minus 1 by Tr. The integration of dt is t plus c, where c is the constant of integration, where c is equal to constant of integration. Now, at t is equal to 0, v is equal to v0. Putting this in the above equation, we get log v0 is equal to minus 1 by tr into 0 plus c, implies as c is equal to log v0. And putting the value of c in this equation, we get log v is equal to minus 1 by t plus log v0, which implies as log v minus log v0 is equal to minus t by tr, implies as log v by v0 is equal to minus t by tr, or implies as v by v0 is equal to e to the power minus t by tr, implies as v is equal to v0 into e to the power minus t by tr. This is the expression for the velocity in damped harmonic oscillation, and we have discussed previously that the time duration within which the velocity becomes 1 by e times its initial velocity, then that time interval will be termed as your relaxation time. So, let us discuss here at t is equal to tr. At t is equal to tr, this expression becomes as v equal to v0 e to the power minus t by t, which is equal to v0 e to the power minus 1, implies as v is equal to v0 by e. Hence, the time interval at which the velocity becomes 1 by e times the initial velocity is known as the relaxation time. The time interval within which the velocity becomes 1 by e times the initial velocity is known as relaxation time. Also, we know that m by r is equal to 1 by 2k and Tr is equal to m by r. So, Tr is equal to 1 by 2k, where Tr is the relaxation time and k is the damping constant. Here we have discussed relaxation time. The only term remained is the modulus of decay or damping constant. Modulus of decay or damping constant. Then what is modulus of decay or damping constant? It is the factor which represents the decrease of oscillation due to damping. Modulus of decay or damping constant is the factor which represents the decrease of oscillation due to damping, because we know in case of damped oscillation the amplitude gradually decreases and also the oscillation gradually decreases and finally becomes 0, and the amplitude gradually decreases. So, what is modulus of decay or a damping constant? Now, it is the amplitude of a vibration which reduces by 1 by e times its original value. That means, damping constant or modulus of decay is the time during which the amplitude of oscillation becomes 1 by e times its original or initial value. That means, at t is equal to Tm, that means modulus of decay, your R is equal to R0 by E, or if we take A as amplitude, then A will be A0 by E. So, to find this condition, let us start with, in case of damped oscillation, what we know, R is equal to R0 e to the power IPT. Previously, in our discussion, we had taken y is equal to A e to the power IPT. Here let us take R is equal to R0 e to the power minus KT. As we have discussed, at a t is equal to Tm, R becomes R0 by E, hence this equation becomes as R0 by E is equal to R0 e to the power minus K Tm, which implies as e to the power minus 1 is equal to e to the power minus K Tm, which implies as K Tm is equal to 1, which implies as Tm, that is modulus of decay, is equal to 1 by K. But R by M is equal to 2K. So, 1 by K is equal to 2 M by R, but this 1 by K is nothing but Tm, implies as Tm is equal to 2 into M by R, and M by R is nothing but Tr, relaxation time. So, this is Tr, that is modulus of decay is twice the relaxation time, which implies as the ratio of modulus of decay and the relaxation time is 2. That is modulus of decay is twice the relaxation time. Okay friends, here we have discussed relaxation time and modulus of decay or damping constant, and hereby we finish our discussions regarding some important terms connected to forced vibration. Many thanks to all of you.